We're going to try to look at a differential equation on my graphics pad today. I don't know how this is going to work, but we're going to try it. This is a problem from our textbook, page 288, problem 11, and it's a system of differential equations. I have an equation in x, as you can see, and it also has a y term in it. And I've got an equation, y prime equals, and it's also got x and y terms. And I have an initial condition for x and an initial condition for y, again, as you can see there. So let's take off and see what we can do with these. And we're going to kind of work on these one at a time. We're going to start by taking the Laplace of both equations and both sides. Now when we start on the x prime equals, we're using theorem 1, which is about derivatives, and it says that the Laplace of x prime is going to be s times the Laplace of x of t minus x of 0, which is minus 1. And that would be equal to 2, and here would be using the linearity, Laplace of x of t plus the Laplace of y of t. Now let's apply the same kind of work to the second equation, and we would have 2 Laplace y of t minus a negative 2 would make that a plus 2 is equal to 6 Laplace x of t plus 3 Laplace y of t. Well, that was a little laborious to write, but this would be a system then, and we would want a simultaneous solution for those two. Now, it will just make the writing easier if we will recall that by convention we write capital X as the Laplace of lowercase x. Now this would be x of t and this would be x of s, and so there is a difference, but I hope you remember all that. So let's rewrite this using this notion, and it makes these things easier, I think, to see. So we'd have s, and then this would be a capital X minus 1 is equal to 2x plus capital Y. And this second equation would be s y plus 2 is equal to 6x plus 3y. And those are the simultaneous equations. Now, if we'll just do the algebra and solve these, we'll find that x is equal to s minus 5 over s squared minus 5s. And if I factor in s out of both terms in the denominator, I get a s outside, s minus 5. The s minus 5's cancel, and it's a 1 over s. And y will be equal to s minus 2 x minus 1, or y would be equal to s minus 2. Now we've solved for x already, and we see that x is equal to 1 over s. So this would be 1 over s minus 1 scroll up if I can find the scroll button. And then y would be equal to, distribute this multiplication 1 over s, and you get 1 minus 2 over s minus 1 is equal to negative 2 over s. So putting these things together then, we've got the Laplace of x of t is equal to 1 over s, and we've got the Laplace of y of t is equal to negative 2 over s. And so applying Laplace inverse, we find that x of t is equal to 1, just the constant. Remember, the first Laplace we looked at was the Laplace of the constant function, x of t equal 1, and its Laplace was 1 over s. And then using linearity here, I see that y of t, if the Laplace of y of t is negative 2 over s, that's negative 2 times 1 over s, and the Laplace of 1 over s is just 1, so this would be negative 2. So the solution, the simultaneous solution, would be two constant functions, x of t equal 1 and y of t is equal to 2. But that's how that worked out, so that wasn't very difficult. Now we want to take a look at partial fractions. You've studied partial fractions before. It's part of the Calculus 2 curriculum, because sometimes in calculus we need to integrate, and we would have a rational function that would be of the form p of x over q of x, p and q being polynomials, p of degree less than or equal to q of x. And if we can write this as a sum, then we can maybe find an easier way to integrate. Well, we're not looking at partial fractions for that purpose, but we are occasionally hit with a Laplace f of x, not x but s, f of s that's a rational function, and if we can express it as a sum of simpler fractions, then that usually leads to an easier job of finding the inverse Laplace. Now, as an example, let's look at f of s is equal to 1 over s to the 4th power minus 16. Now, if I would look through my mind and through the tables in the inside front cover of my textbook, this is not the Laplace of any function that's listed in that table. So if I can change the form of 1 over s squared minus 16, maybe I can recognize a sum of Laplaces and come up with an easy way to calculate the inverse Laplace of f of s. Well, we see right away that this thing, the denominator, will factor, and that would factor into 1 over s squared minus 4 s squared plus 4. And that factoring form you learned in elementary algebra called the difference of squares, perfect square, and the difference is a minus. Now I've got the difference of squares again in this factor, but this is not the difference. This is the sum of squares, and that's called an irreducible quadratic factor. You can't factor this further. Now, what do we do with those? Well, just as a refresher, because you've seen this in Calculus 3, we would look on page 289 and read the following pages, because it's all about partial fractions. This is section 4.3 of our textbook, page 289. And those theorems, or they're really rules, those rules will tell you that if I'm going to reduce this to a sum of partial fractions, this is an irreducible quadratic factor. So if I have an irreducible quadratic factor, I should expect in my sum of partial fractions, I'm going to write this one down explicitly, to have a numerator of the form ax plus b. And if I have linear factors like s minus 2, then I should expect in the numerator to have a constant c, and to have a c over s minus 2 in the expression that's a sum of partial fractions that's equal to this ratio. All right, now that's not very precise, but you'll read your textbook and you'll get the more precise definitions there. And what we're doing is refreshing our memory. So I think a quick read and we'll be okay. Now, what if we wanted to find, let's see, let's say we want to find f of t where f of s is equal to 1 over s4 minus 16. And in fact, this is problem number 17 at end of section 4.3. Well, I don't recognize 1 over s squared minus 4 as being the Laplace transform of any elementary function. And I consult my table of functions and I don't find it there either. However, I do notice, as we've noticed right here, that I can factor, at least partially, I can factor 1 over s squared minus 16 into this fraction ratio where the denominator has got an s squared minus 4 and an s squared plus 4. And if I look again in the tables, I see that there is an elementary function that has a Laplace of s squared plus k squared, and there's another that has a denominator of s squared minus k squared. So if I keep that in mind, if I had a sum of partial fractions where these were the denominators, then I could use the table on the inside front cover and I could come up with the function that this is the Laplace of. Now again, it takes a little experience and practice, but I cannot introduce a variable s into the numerator here, because again, like taking integrals, you can always introduce a constant under the integral, but you can't introduce a variable. So I can't just introduce that, can't do that, but I could introduce a constant. Well, that's what makes me think that the two functions I'm aiming to use here are going to be sin h, the hyperbolic sign, and sin, the trig function sign. And look inside the front cover of your textbook and you'll see what I mean. These two have denominators that look like this, but they've got constants in the numerators, and it's no problem introducing a constant. So that kind of leads you to some insight into the strategy we're going to use here. Now let's use some of the theory of partial fractions. And we've already got a start up here where we've taken the denominator s to the fourth minus 16 and factored it this way. I know I could factor this one further, but when I look at the hyperbolic sign and the sine function, I see that the denominators are these denominators. And so I probably don't want to factor this further. Let's just leave it like it is. Now, what does that bring us to? Well, that brings me to 1 over, and I'm going to write it as s squared minus 4, s squared plus 4. Now, using the two rules in this section, I know that I've got quadratic factors, and so this is going to be ax plus b. A and b are determinable, but they're not determined right now. S squared minus 4 plus, and then this would be a irreducible quadratic factor, so we'd have a cx plus d over s squared plus 4. Now, if I can determine a, b, c, and d, then I've written this as a sum of partial fractions, and that's going to be our goal for the next few minutes. Well, again, remembering from calculus, what you would do next would probably be to multiply this equation by s squared minus 4 times s squared plus 4, and you would obtain 1 is equal to, now when I take this denominator and use it as a multiplier, the s squared minus 4 is going to cancel, so I would have an ax plus b, and then it would be times an s squared plus 4. And then what would I have over here? I would have a cx plus d times an s squared minus 4. So this is kind of a key equation. We're going to use this to see if we can't come up with a scheme for finding A, B, C, and D right here. Let me scroll up. Now I'm going to skip quite a bit of the algebra because I know you're very good at algebra. But one of the things I can do would be to, since this is an identity, it would be true for all values of the variable. I also notice that I've got a small mistake in here. In place of having an x as the variable, that we're working in s, and so that would be a variable s, and that would be a variable s, and so I've corrected that now. Don't let it confuse you. If I would let s equal, for example, if I would let s equal 2, well then when I substitute it over here, I'd have a 4 minus 4. That would be a 0. This whole term would drop out, and I would have the equation 1 is equal to, now if s is 2, this would be a 2a plus b, and this would be 4 plus 4 would be 8, and this whole thing would be 0 because if s is 2, then I've got a factor of 0 in here. Now we can try other values of s to see if we can't simplify this key equation, and the values I used were s equal 1, s equals 0, and s equal negative 2. Other values would work, but using those, I found equations, and I'm not going to solve these on the fly here, but I found other equations that were 1 is equal to a plus b times 5 plus c plus d times negative 3. Now, where did the s go? Where did the s go? Well, if s is equal to 1, then it's an a plus b. And then using s equals 0, I came up with 1 is equal to 4b minus 4d, and using s equal negative 2, 1 is equal to negative 2a plus b times 8. Now if we would clean these up, now I've got 4 equations in 4 unknowns, a, b, c, and d. If I clean those up, and I want to not take time to do that with you, because I know you're quite capable of doing that, we can solve, and I put these equations in a matrix and took the inverse of the matrix using my calculator, or one could use Wolfram Alpha or Maple, but we come up with A is equal to 0, B is equal to 1/8, C is equal to 0, and D is equal to negative 1/8. And what that tells me is that f of s is equal to, remember this was as plus b, a is 0, b is 1/8, so I've got a 1/8 over s squared minus 4. 4 is 2 squared. And then this would be plus, and the numerator in the second term was cx plus d. If c is 0, this gives me a negative 1/8 over s squared plus 4. All right, well, happy days are almost here, because this looks like the hyperbolic sines. It's almost, but not quite perfect, but it's the hyperbolic sines Laplace, and this is the sines Laplace, almost, but not perfectly. So let's do a little more algebra, and I'm consulting, at least in my mind's eye, with the inside front cover, and I'm seeing that I've got a 1/8, and I know that I need, since this is s squared minus 2 squared, I know I need a 2 on the numerator. Well, let's just put a 1/2 out here and a 2 in the numerator, and an s squared minus 2 squared there. And then a minus 1/8, and I know that again in this numerator I need a 2 because this is s squared plus 2 squared, so I'll put a 1/2 out here and a 2 in that numerator, and an s squared plus 2 squared. So this is 1/16, and this is the Laplace of the hyperbolic sine of 2t. And this piece is the Laplace, not the negative 1/16, but this thing in here is the Laplace of the sine of 2t. So if the Laplace of f of t is equal to this expression, then I can see that f of t would be equal to, this would be 1/16 sin h hyperbolic sine of 2t minus 1/16 sine of 2t. So I think that's all correct. Go through it a piece at a time and see if you can't get the same result. Thank you.